OK, welcome back, everyone, to an introduction to artificial intelligence with Python. And now, so far, we've taken a look at a couple of different types of problems. We've seen classical search problems where we're trying to get from an initial state to a goal by figuring out some optimal path. We've taken a look at adversarial search, where we have a game-playing agent that is trying to make the best move. We've seen knowledge-based problems where we're trying to use logic and inference to be able to figure out and draw some additional conclusions. And we've seen some probabilistic models as well, where we might not have certain information about the world, but we want to use the knowledge about probabilities that we do have to be able to draw some conclusions. Today, we're going to turn our attention to another category of problems generally known as optimization problems, where optimization is really all about choosing the best option from a set of possible options. And we've already seen optimization in some contexts, like game playing, where we're trying to create an AI that chooses the best move out of a set of possible moves. But what we'll take a look at today is a category of types of problems and algorithms to solve them that can be used in order to deal with a broader range of potential optimization problems. And the first of the algorithms that we'll take a look at is known as local search. And local search differs from search algorithms we've seen before in the sense that the search algorithms we've looked at so far, which are things like breadth-first search or A-star search, for example, generally maintain a whole bunch of different paths that we're simultaneously exploring, and we're looking at a bunch of different paths at once, trying to find our way to the solution. On the other hand, in local search, this is going to be a search algorithm that's really just going to maintain a single node, looking at a single state. And we'll generally run this algorithm by maintaining that single node and then moving ourselves to one of the neighboring nodes throughout this search process. And this is generally useful in contexts not like these problems, which we've seen before, like a maze-solving situation where we're trying to find our way from the initial state to the goal by following some path. But local search is most applicable when we really don't care about the path at all, and all we care about is what the solution is. And in the case of solving a maze, the solution was always obvious. You could point to the solution. You know exactly what the goal is. And the real question is, what is the path to get there? But local search is going to come up in cases where figuring out exactly what the solution is, exactly what the goal looks like, is actually the heart of the challenge. And to give an example of one of these kinds of problems, we'll consider a scenario where we have two types of buildings, for example. We have houses and hospitals. And our goal might be, in a world that's formatted as this grid, where we have a whole bunch of houses, a house here, two houses over there, maybe we want to try and find a way to place two hospitals on this map. So maybe a hospital here and a hospital there. And the problem now is we want to place two hospitals on the map, but we want to do so with some sort of objective. And our objective in this case is to try and minimize the distance of any of the houses from a hospital. So you might imagine, all right, what's the distance from each of the houses to their nearest hospital? There are a number of ways we could calculate that distance. But one way is using a heuristic we've looked at before, which is the Manhattan distance, this idea of how many rows and columns would you have to move inside of this grid layout in order to get to a hospital, for example. And it turns out if you take each of these four houses and figure out, all right, how close are they to their nearest hospital, you get something like this, where this house is 3 away from a hospital, this house is 6 away, these two houses are each 4 away. And if you add all those numbers up together, you get a total cost of 17, for example. So for this particular configuration of hospitals, a hospital here and a hospital there, that state, we might say, has a cost of 17. And the goal of this problem now that we would like to apply a search algorithm to figure out is, can you solve this problem to find a way to minimize that cost, minimize the total amount? If you sum up all of the distances from all the houses to the nearest hospital, how can we minimize that final value? And if we think about this problem a little bit more abstractly, abstracting away from this specific problem and thinking more generally about problems like it, you can often formulate these problems by thinking about them as a state space landscape, as we'll soon call it. Here in this diagram of a state space landscape, each of these vertical bars represents a particular state that our world could be in. So for example, each of these vertical bars represents a particular configuration of two hospitals. And the height of this vertical bar is generally going to represent some function of that state, some value of that state. So maybe in this case, the height of the vertical bar represents what is the cost of this particular configuration of hospitals in terms of what is the sum total of all of the distances from all of the houses to their nearest hospital. And generally speaking, when we have a state space landscape, we want to do one of two things. We might be trying to maximize the value of this function, trying to find a global maximum, so to speak, of this state space landscape, a single state whose value is higher than all of the other states that we could possibly choose from. And generally, in this case, when we're trying to find a global maximum, we'll call the function that we're trying to optimize some objective function, some function that measures for any given state how good is that state, such that we can take any state, pass it into the objective function, and get a value for how good that state is. And ultimately, what our goal is to find one of these states that has the highest possible value for that objective function. An equivalent but reversed problem is the problem of finding a global minimum, some state that has a value after you pass it into this function that is lower than all of the other possible values that we might choose from. And generally speaking, when we're trying to find a global minimum, we call the function that we're calculating a cost function. Generally, each state has some sort of cost, whether that cost is a monetary cost or a time cost, or in the case of the houses and hospitals we've been looking at just now, a distance cost in terms of how far away each of the houses is from a hospital. And we're trying to minimize the cost, find the state that has the lowest possible value of that cost. So these are the general types of ideas that we might be trying to go for within a state space landscape, trying to find a global maximum or trying to find a global minimum. And how exactly do we do that? We'll recall that in local search, we generally operate this algorithm by maintaining just a single state, just some current state represented inside of some node, maybe inside of a data structure, where we're keeping track of where we are currently. And then ultimately what we're going to do is from that state, move to one of its neighbor states. So in this case, represented in this one-dimensional space by just the state immediately to the left or to the right of it. But for any different problem, you might define what it means for there to be a neighbor of a particular state. In the case of the hospitals, for example, that we were just looking at, a neighbor might be moving one hospital one space to the left or to the right or up or down. Some state that is close to our current state, but slightly different, and as a result, might have a slightly different value in terms of its objective function or in terms of its cost function. So this is going to be our general strategy in local search, to be able to take a state, maintaining some current node, and move where we're looking at in this state space landscape in order to try to find a global maximum or a global minimum somehow. And perhaps the simplest of algorithms that we could use to implement this idea of local search is an algorithm known as hill climbing. And the basic idea of hill climbing is, let's say I'm trying to maximize the value of my state. I'm trying to figure out where the global maximum is. I'm going to start at a state. And generally, what hill climbing is going to do is it's going to consider the neighbors of that state. That from this state, all right, I could go left or I could go right. And this neighbor happens to be higher and this neighbor happens to be lower. And in hill climbing, if I'm trying to maximize the value, I'll generally pick the highest one I can. Between the state to the left and right of me, this one is higher. So I'll go ahead and move myself to consider that state instead. And then I'll repeat this process, continually looking at all of my neighbors and picking the highest neighbor, doing the same thing, looking at my neighbors, picking the highest of my neighbors, until I get to a point like right here, where I consider both of my neighbors, and both of my neighbors have a lower value than I do. This current state has a value that is higher than any of its neighbors. And at that point, the algorithm terminates, and I can say, all right, here I have now found the solution. And the same thing works in exactly the opposite way for trying to find a global minimum. But the algorithm is fundamentally the same. If I'm trying to find a global minimum and say my current state starts here, I'll continually look at my neighbors, pick the lowest value that I possibly can, until I eventually, hopefully, find that global minimum, a point at which, when I look at both of my neighbors, they each have a higher value, and I'm trying to minimize the total score or cost or value that I get as a result of calculating some sort of cost function. So we can formulate this graphical idea in terms of pseudocode. And the pseudocode for hill climbing might look like this. We define some function called hill climb that takes as input the problem that we're trying to solve. And generally, we're going to start in some sort of initial state. So I'll start with a variable called current that is keeping track of my initial state, like an initial configuration of hospitals. And maybe some problems lend themselves to an initial state, some place where you begin. In other cases, maybe not, in which case we might just randomly generate some initial state, just by choosing 2 locations for hospitals at random, for example, and figuring out from there how we might be able to improve. But that initial state, we're going to store inside of current. And now here comes our loop, some repetitive process we're going to do again and again until the algorithm terminates. And what we're going to do is first say, let's figure out all of the neighbors of the current state. From my state, what are all of the neighboring states for some definition of what it means to be a neighbor? And I'll go ahead and choose the highest valued of all of those neighbors and save it inside of this variable called neighbor. So we'll keep track of the highest valued neighbor. This is in the case where I'm trying to maximize the value. In the case where I'm trying to minimize the value, you might imagine here you'll pick the neighbor with the lowest possible value. But these ideas are really fundamentally interchangeable. And it's possible in some cases there might be multiple neighbors that each have an equally high value or an equally low value in the minimizing case. And in that case, we can just choose randomly from among them. Just choose one of them and save it inside of this variable neighbor. And then the key question to ask is this neighbor better than my current state? And if the neighbor, the best neighbor that I was able to find, is not better than my current state, well, then the algorithm is over. And I'll just go ahead and return the current state. If none of my neighbors are better, then I may as well stay where I am, is the general logic of the hill climbing algorithm. But otherwise, if the neighbor is better, then I may as well move to that neighbor. So you might imagine setting current equal to neighbor, where the general idea is if I'm at a current state and I see a neighbor that is better than me, then I'll go ahead and move there. And then I'll repeat the process, continually moving to a better neighbor until I reach a point at which none of my neighbors are better than I am. And at that point, we'd say the algorithm can just terminate there. So let's take a look at a real example of this with these houses and hospitals. So we've seen now that if we put the hospitals in these two locations, that has a total cost of 17. And now we need to define, if we're going to implement this hill climbing algorithm, what it means to take this particular configuration of hospitals, this particular state, and get a neighbor of that state. And a simple definition of neighbor might be just, let's pick one of the hospitals and move it by one square, to the left or right or up or down, for example. And that would mean we have 6 possible neighbors from this particular configuration. We could take this hospital and move it to any of these 3 possible squares, or we take this hospital and move it to any of those 3 possible squares. And each of those would generate a neighbor. And what I might do is say, all right, here's the locations and the distances between each of the houses and their nearest hospital. Let me consider all of the neighbors and see if any of them can do better than a cost of 17. And it turns out there are a couple of ways that we could do that. And it doesn't matter if we randomly choose among all the ways that are the best. But one such possible way is by taking a look at this hospital here and considering the directions in which it might move. If we hold this hospital constant, if we take this hospital and move it 1 square up, for example, that doesn't really help us. It gets closer to the house up here, but it gets further away from the house down here. And it doesn't really change anything for the 2 houses along the left-hand side. But if we take here, and it doesn't really change, and move it 1 square down, it's the opposite problem. It gets further away from the house up above, and it gets closer to the house down below. The real idea, the goal should be to be able to take this hospital and move it 1 square to the left. By moving it 1 square to the left, we move it closer to both of these houses on the right without changing anything about the houses on the left. For them, this hospital is still the closer one, so they aren't affected. So we're able to improve the situation by picking a neighbor that results in a decrease in our total cost. And so we might do that, move ourselves from this current state to a neighbor by just taking that hospital and moving it. And at this point, there's not a whole lot that can be done with this hospital, but there's still other optimizations we can make, other neighbors we can move to that are going to have a better value. If we consider this hospital, for example, we might imagine that right now it's a bit far up, that both of these houses are a little bit lower. So we might be able to do better by taking this hospital and moving it 1 square down, moving it down so that now instead of a cost of 15, we're down to a cost of 13 for this particular configuration. And we can do even better by taking the hospital and moving it 1 square to the left. Now instead of a cost of 13, we have a cost of 11, because this house is 1 away from the hospital, this one is 4 away, this one is 3 away, and this one is also 3 away. So we've been able to do much better than that initial cost that we had using the initial configuration, just by taking every state and asking ourselves the question, can we do better by just making small incremental changes, moving to a neighbor, moving to a neighbor, and moving to a neighbor after that? And now at this point, we can potentially see that at this point the algorithm is going to terminate. There's actually no neighbor we can move to that is going to improve the situation, get us a cost that is less than 11. Because if we take this hospital and move it up or to the right, well, that's going to make it further away. If we take it and move it down, that doesn't really change the situation. It gets further away from this house, but closer to that house. And likewise, the same story was true for this hospital. Any neighbor we move it to, up, left, down, or right, is either going to make it further away from the houses and increase the cost, or it's going to have no effect on the cost whatsoever. And so the question we might now ask is this the best we could do? Is this the best placement of the hospitals we could possibly have? And it turns out the answer is no, because there's a better way that we could place these hospitals. And in particular, there are a number of ways you could do this, but one of the ways is by taking this hospital here and moving it to this square, for example, moving it diagonally by one square, which was not part of our definition of neighbor. We could only move left, right, up, or down. But this is, in fact, better. It has a total cost of 9. It is now closer to both of these houses, and as a result, the total cost is less. But we weren't able to find it because in order to get there, we had to go through a state that actually wasn't any better than the current state that we had been on previously. And so this appears to be a limitation or a concern you might have as you go about trying to implement a hill climbing algorithm, is that it might not always give you the optimal solution. If we're trying to maximize the value of any particular state, we're trying to find the global maximum, a concern might be that we could get stuck at one of the local maxima, highlighted here in blue, where a local maxima is any state whose value is higher than any of its neighbors. If we ever find ourselves at one of these two states when we're trying to maximize the value of the state, we're not going to make any changes. We're not going to move left or right. We're not going to move left here, because those states are worse. But yet we haven't found the global optimum. We haven't done as best as we could do. And likewise, in the case of the hospitals, what we're ultimately trying to do is find a global minimum, find a value that is lower than all of the others. But we have the potential to get stuck at one of the local minima, any of these states whose value is lower than all of its neighbors, but still not as low as the local minima. And so the takeaway here is that it's not always going to be the case that when we run this naive hill climbing algorithm, that we're always going to find the optimal solution. There are things that could go wrong. If we started here, for example, and tried to maximize our value as much as possible, we might move to the highest possible neighbor, move to the highest possible neighbor, move to the highest possible neighbor, and stop, and never realize that there's actually a better state way over there that we could have gone to instead. And other problems you might imagine, just by taking a look at this state space landscape, are these various different types of plateaus. Something like this flat local maximum here, where all 6 of these states each have the exact same value. And so in the case of the algorithm we showed before, none of the neighbors are better, so we might just get stuck at this flat local maximum. And even if you allowed yourself to move to one of the neighbors, it wouldn't be clear which neighbor you would ultimately move to, and you could get stuck here as well. And there's another one over here. This one is called a shoulder. It's not really a local maximum because there's still places where we can go higher, not a local minimum because we can go lower. So we can still make progress, but it's still this flat area, where if you have a local search algorithm, there's potential to get lost here, unable to make some upward or downward progress, depending on whether we're trying to maximize or minimize, and therefore another potential for us to be able to find a solution that might not actually be the optimal solution. And so because of this potential, the potential that hill climbing has to not always find us the optimal result, it turns out there are a number of different varieties and variations on the hill climbing algorithm that help to solve the problem better depending on the context. And depending on the specific type of problem, some of these variants might be more applicable than others. What we've taken a look at so far is a version of hill climbing generally called steepest ascent hill climbing, where the idea of steepest ascent hill climbing is we are going to choose the highest valued neighbor in the case where we're trying to maximize, or the lowest valued neighbor in cases where we're trying to minimize. But generally speaking, if I have 5 neighbors and they're all better than my current state, I will pick the best one of those 5. Now, sometimes that might work pretty well. It's sort of a greedy approach of trying to take the best operation at any particular time step. But it might not always work. There might be cases where actually I want to choose an option that is slightly better than me, but maybe not the best one, because that later on might lead to a better outcome ultimately. So there are other variants that we might consider of this basic hill climbing algorithm. One is known as stochastic hill climbing. And in this case, we choose randomly from all of our higher valued neighbors. So if I'm at my current state and there are 5 neighbors that are all better than I am, rather than choosing the best one, as steepest ascent would do, stochastic will just choose randomly from one of them, thinking that if it's better, then it's better, and maybe there's a potential to make forward progress, even if it is not locally the best option I could possibly choose. First choice hill climbing ends up just choosing the very first highest valued neighbor that it follows, behaving on a similar idea, rather than consider all of the neighbors. As soon as we find a neighbor that is better than our current state, we'll go ahead and move there. So maybe some efficiency improvements there, and maybe has the potential to find a solution that the other strategies weren't able to find. And with all of these variants, we still suffer from the same potential risk, this risk that we might end up at a local minimum or a local maximum. And we can reduce that risk by repeating the process multiple times. So one variant of hill climbing is random restart hill climbing, where the general idea is we'll conduct hill climbing multiple times. If we apply steepest descent hill climbing, for example, we'll start at some random state, try and figure out how to solve the problem, and figure out what is the local maximum or local minimum we get to. And then we'll just randomly restart and try again. Choose a new starting configuration, try and figure out what the local maximum or minimum is, and do this some number of times. And then after we've done it some number of times, we can pick the best one out of all of the ones that we've taken a look at. So there's another option we have access to as well. And then, although I said that generally local search will usually just keep track of a single node and then move to one of its neighbors, there are variants of hill climbing that are known as local beam searches, where rather than keep track of just one current best state, we're keeping track of k highest valued neighbors, such that rather than starting at one random initial configuration, I might start with 3 or 4 or 5, randomly generate all the neighbors, and then pick like the 3 or 4 or 5 best of all of the neighbors that I find, and continually repeat this process, with the idea being that now I have more options that I'm considering, more ways that I could potentially navigate myself to the optimal solution that might exist for a particular problem. So let's now take a look at some actual code that can implement some of these kinds of ideas, something like steepest ascent hill climbing, for example, for trying to solve this hospital problem. So I'm going to go ahead and go into my hospitals directory, where I've actually set up the basic framework for solving this type of problem. I'll go ahead and go into hospitals.py, and we'll take a look at the code we've created here. I've defined a class that is going to represent the state space. So the space has a height and a width, and also some number of hospitals. So you can configure how big is your map, how many hospitals should go here. We have a function for adding a new house to the state space, and then some functions that are going to get me all of the available spaces for if I want to like randomly place hospitals in particular locations. And here now is the hill climbing algorithm. So what are we going to do in the hill climbing algorithm? Well, we're going to start by randomly initializing where the hospitals are going to go. We don't know where the hospitals should actually be, so let's just randomly place them. So here I'm running a loop for each of the hospitals that I have. I'm going to go ahead and add a new hospital at some random location. So I basically get all of the available spaces, and I randomly choose one of them as where I would like to add this particular hospital. I have some logging output and generating some images, which we'll take a look at a little bit later. But here is the key idea. So I'm going to just keep repeating this algorithm. I could specify a maximum of how many times I want it to run, or I could just run it up until it hits a local maximum or local minimum. And now we'll basically consider all of the hospitals that could potentially move. So consider each of the 2 hospitals or more hospitals if there are more than that. And consider all of the places where that hospital could move to, some neighbor of that hospital that we can move the neighbor to. And then see, is this going to be better than where we were currently? So if it is going to be better, then we'll go ahead and update our best neighbor and keep track of this new best neighbor that we found. And then afterwards, we can ask ourselves the question, if best neighbor cost is greater than or equal to the cost of the current set of hospitals, meaning if the cost of our best neighbor is greater than the current cost, meaning our best neighbor is worse than our current state, well, then we shouldn't make any changes at all, and we should just go ahead and return the current set of hospitals. But otherwise, we can update our hospitals in order to change them to one of the best neighbors. And if there are multiple that are all equivalent, I'm here using random.choice to say go ahead and choose one randomly. So this is really just a Python implementation of that same idea that we were just talking about, this idea of taking a current state, some current set of hospitals, generating all of the neighbors, looking at all of the ways we could take one hospital and move it 1 square to the left or right or up or down, and then figuring out, based on all of that information, which is the best neighbor or the set of all the best neighbors, and then choosing from one of those. And each time we go ahead and generate an image in order to do that. And so now what we're doing is if we look down at the bottom, I'm going to randomly generate a space with height 10 and width 20, and I'll say go ahead and put 3 hospitals somewhere in the space. I'll randomly generate 15 houses that I just go ahead and add in random locations. And now I'm going to run this hill climbing algorithm in order to try and figure out where we should place those hospitals. So I'll go ahead and run this program by running Python hospitals. And we see that we started. Our initial state had a cost of 72, but we were able to continually find neighbors that were able to decrease that cost, decrease to 69, 66, 63, so on and so forth, all the way down to 53 as the best neighbor we were able to ultimately find. And we can take a look at what that looked like by just opening up these files. So here, for example, was the initial configuration. We randomly selected a location for each of these 15 different houses, and then randomly selected locations for 1, 2, 3 hospitals that were just located somewhere inside of this state space. And if you add up all the distances from each of the houses to their nearest hospital, you get a total cost of about 72. And so now the question is, what neighbors can we move to that improve the situation? And it looks like the first one the algorithm found was by taking this house that was over there on the right and just moving it to the left. And that probably makes sense because if you look at the houses in that general area, really these 5 houses look like they're probably the ones that are going to be closest to this hospital over here. Moving it to the left decreases the total distance, at least to most of these houses, though it does increase that distance for one of them. And so we're able to make these improvements to the situation by continually finding ways that we can move these hospitals around until we eventually settle at this particular state that has a cost of 53, where we figured out a position for each of the hospitals, and now none of the neighbors that we could move to are actually going to improve the situation. We can take this hospital and that hospital and look at each of the neighbors, and none of those are going to be better than this particular configuration. And again, that's not to say that this is the best we could do. There might be some other configuration of hospitals that is a global minimum, and this might just be a local minimum that is the best of all of its neighbors, but maybe not the best in the entire possible state space. And you could search through the entire state space by considering all of the possible configurations for hospitals, but ultimately that's going to be very time intensive, especially as our state space gets bigger and there might be more and more possible states. It's going to take quite a long time to look through all of them. And so being able to use these sort of local search algorithms can often be quite good for trying to find the best solution we can do, and especially if we don't care about doing the best possible and we just care about doing pretty good and finding a pretty good placement of those hospitals, then these methods can be particularly powerful. But of course, we can try and mitigate some of this concern by, instead of using hill climbing, to use random restart. This idea of rather than just hill climb one time, we can hill climb multiple times and say, try hill climbing a whole bunch of times on the exact same map and figure out what is the best one that we've been able to find. And so I've here implemented a function for random restart that restarts some maximum number of times. And what we're going to do is repeat that number of times this process of just go ahead and run the hill climbing algorithm, figure out what the cost is of getting from all the houses to the hospitals, and then figure out, is this better than we've done so far? So I can try this exact same idea, where instead of running hill climbing, I'll go ahead and run random restart, and I'll randomly restart maybe 20 times, for example. And we'll go ahead and now I'll remove all the images and then rerun the program. And now we started by finding an original state. When we initially ran hill climbing, the best cost we were able to find was 56. Each of these iterations is a different iteration of the hill climbing algorithm. We're running hill climbing not one time, but 20 times here, each time going until we find a local minimum, in this case. And we look and see each time, did we do better than we did the best time we've done so far? So we went from 56 to 46. This one was greater, so we ignored it. This one was 41, which was less, so we went ahead and kept that one. And for all of the remaining 16 times that we tried to implement hill climbing, and we tried to run the hill climbing algorithm, we couldn't do any better than that 41. Again, maybe there is a way to do better that we just didn't find, but it looks like that way ended up being a pretty good solution to the problem. That was attempt number 3, starting from counting at 0. So we can take a look at that, open up number 3, and this was the state that happened to have a cost of 41. That after running the hill climbing algorithm on some particular random initial configuration of hospitals, this is what we found was the local minimum in terms of trying to minimize the cost. And it looks like we did pretty well, that this hospital is pretty close to this region. This one is pretty close to these houses here. This hospital looks about as good as we can do for trying to capture those houses over on that side. And so these sorts of algorithms can be quite useful for trying to solve these problems. But the real problem with many of these different types of hill climbing, steepest ascent, stochastic first choice, and so forth, is that they never make a move that makes our situation worse. Right? They're always going to take ourselves in our current state, look at the neighbors, and consider, can we do better than our current state, and move to one of those neighbors. Which of those neighbors we choose might vary among these various different types of algorithms, but we never go from a current position to a position that is worse than our current position. And ultimately, that's what we're going to need to do if we want to be able to find a global maximum or a global minimum. Because sometimes if we get stuck, we want to find some way of dislodging ourselves from our local maximum or local minimum in order to find the global maximum or the global minimum, or increase the probability that we do find it. And so the most popular technique for trying to approach the problem from that angle is a technique known as simulated annealing. Simulated because it's modeling after a real physical process of annealing, where you can think about this in terms of physics, a physical situation where you have some system of particles. And you might imagine that when you heat up a particular physical system, there's a lot of energy there. Things are moving around quite randomly. But over time, as the system cools down, it eventually settles into some final position. And that's going to be the general idea of simulated annealing. We're going to simulate that process of some high temperature system where things are moving around randomly quite frequently, but over time decreasing that temperature until we eventually settle at our ultimate solution. And the idea is going to be, if we have some state space landscape that looks like this, and we begin at an initial state here, if we're looking for a global maximum, and we're trying to maximize the value of the state, our traditional hill climbing algorithms would just take the state and look at the two neighbor ones and always pick the one that is going to increase the value of the state. But if we want some chance of being able to find the global maximum, we can't always make good moves. We have to sometimes make bad moves and allow ourselves to make a move in a direction that actually seems, for now, to make our situation worse, such that later we can find our way up to that global maximum in terms of trying to solve that problem. Of course, once we get up to this global maximum, once we've done a whole lot of the searching, then we probably don't want to be moving to states that are worse than our current state. And so this is where this metaphor for annealing starts to come in, where we want to start making more random moves, and over time start to make fewer of those random moves based on a particular temperature schedule. So the basic outline looks something like this. Early on in simulated annealing, we have a higher temperature state. And what we mean by a higher temperature state is that we are more likely to accept neighbors that are worse than our current state. That we might look at our neighbors, and if one of our neighbors is worse than the current state, especially if it's not all that much worse, if it's pretty close but just slightly worse, then we might be more likely to accept that and go ahead and move to that neighbor anyways. But later on, as we run simulated annealing, we're going to decrease that temperature. And at a lower temperature, we're going to be less likely to accept neighbors that are worse than our current state. Now, to formalize this and put a little bit of pseudocode to it, here is what that algorithm might look like. We have a function called simulated annealing that takes as input the problem we're trying to solve, and also potentially some maximum number of times that we might want to run the simulated annealing process. How many different neighbors are we going to try and look for? And that value is going to vary based on the problem you're trying to solve. We'll again start with some current state that will be equal to the initial state of the problem. But now we need to repeat this process over and over for max number of times. Repeat some process some number of times, where we're first going to calculate a temperature. And this temperature function takes the current time t, starting at 1, going all the way up to max, and then gives us some temperature that we can use in our computation, where the idea is that this temperature is going to be higher early on, and it's going to be lower later on. So there are a number of ways this temperature function could often work. One of the simplest ways is just to say it is like the proportion of time that we still have remaining. Out of like max units of time, how much time do we have remaining? You start off with a lot of that time remaining, and as time goes on, the temperature is going to decrease because you have less and less of that remaining time still available to you. So we calculate a temperature for the current time. And then we pick a random neighbor of the current state. No longer are we going to be picking the best neighbor that we possibly can, or just one of the better neighbors that we can. We're going to pick a random neighbor. It might be better, it might be worse, but we're going to calculate that. We're going to calculate delta E for energy in this case, which is just how much better is the neighbor than the current state. So if delta E is positive, that means the neighbor is better than our current state. If delta E is negative, that means the neighbor is worse than our current state. And so we can then have a condition that looks like this. If delta E is greater than 0, that means the neighbor state is better than our current state. And if ever that situation arises, we'll just go ahead and update current to be that neighbor. Same as before, move where we are currently to be the neighbor, because the neighbor is better than our current state. We'll go ahead and accept that. But now the difference is that whereas before we never ever wanted to take a move that made our situation worse, now we sometimes want to make a move that is actually going to make our situation worse, because sometimes we're going to need to dislodge ourselves from a local minimum or local maximum to increase the probability that we're able to find the global minimum or the global maximum a little bit later. And so how do we do that? How do we decide to sometimes accept some state that might actually be worse? Well, we're going to accept a worse state with some probability. And that probability needs to be based on a couple of factors. It needs to be based in part on the temperature, where if the temperature is higher, we're more likely to move to a worse neighbor. And if the temperature is lower, we're less likely to move to a worse neighbor. But it also, to some degree, should be based on delta E. If the neighbor is much worse than the current state, we probably want to be less likely to choose that than if the neighbor is just a little bit worse than the current state. So again, there are a couple of ways you could calculate this, but it turns out one of the most popular is just to calculate e to the power of delta E over t, where e is just a constant. Delta E over t are based on delta E and t here. We calculate that value, and that'll be some value between 0 and 1, and that is the probability with which we should just say, all right, let's go ahead and move to that neighbor. And it turns out that if you do the math for this value, when delta E is such that the neighbor is not that much worse than the current state, that's going to be more likely that we're going to go ahead and move to that state. And likewise, when the temperature is lower, we're going to be less likely to move to that neighboring state as well. So now this is the big picture for simulated annealing. This process of taking the problem and going ahead and generating random neighbors. We'll always move to a neighbor if it's better than our current state. But even if the neighbor is worse than our current state, we'll sometimes move there, depending on how much worse it is, and also based on the temperature. And as a result, the goal of this whole process is that as we begin to try and find our way to the global maximum or the global minimum, we can dislodge ourselves if we ever get stuck at a local maximum or local minimum in order to eventually make our way to exploring the part of the state space that is going to be the best. And then as the temperature decreases, eventually we settle there without moving around too much from what we found to be the globally best thing that we can do thus far. So at the very end, we just return whatever the current state happens to be, and that is the conclusion of this algorithm. We've been able to figure out what the solution is. And these types of algorithms have a lot of different applications. Anytime you can take a problem and formulate it as something where you can explore a particular configuration and then ask, are any of the neighbors better than this current configuration, and have some way of measuring that, then there's an applicable case for these hill climbing simulated annealing types of algorithms. So sometimes it can be for facility location type problems, like for when you're trying to plan a city and figure out where the hospitals should be. But there are definitely other applications as well. And one of the most famous problems in computer science is the traveling salesman problem. Traveling salesman problem generally is formulated like this. I have a whole bunch of cities here indicated by these dots. And what I'd like to do is find some route that takes me through all of the cities and ends up back where I started. So some route that starts here, goes through all these cities, and ends up back where I originally started. And what I might like to do is minimize the total distance that I have to travel in order to, or the total cost of taking this entire path. And you can imagine this is a problem that's very applicable in situations like when delivery companies are trying to deliver things to a whole bunch of different houses. They want to figure out, how do I get from the warehouse to all these various different houses and get back again, all using as minimal time and distance and energy as possible. So you might want to try to solve these sorts of problems. But it turns out that solving this particular kind of problem is very computationally difficult. It is a very computationally expensive task to be able to figure it out. This falls under the category of what are known as NP-complete problems, problems that there is no known efficient way to try and solve these sorts of problems. And so what we ultimately have to do is come up with some approximations, some ways of trying to find a good solution, even if we're not going to find the globally best solution that we possibly can, at least not in a feasible or tractable amount of time. And so what we could do is take the traveling salesman problem and try to formulate it using local search and ask a question like, all right, I can pick some state, some configuration, some route between all of these nodes, and I can measure the cost of that state, figure out what the distance is. And I might now want to try to minimize that cost as much as possible. And then the only question now is, what does it mean to have a neighbor of this state? What does it mean to take this particular route and have some neighboring route that is close to it but slightly different, such that it might have a different total distance? And there are a number of different definitions for what a neighbor of a traveling salesman configuration might look like. But one way is just to say, a neighbor is what happens if we pick two of these edges between nodes and switch them effectively. So for example, I might pick these two edges here, these two that just happen to cross. This node goes here, this node goes there, and go ahead and switch them. And what that process will generally look like is removing both of these edges from the graph, taking this node and connecting it to the node it wasn't connected to, so connecting it up here instead, we'll need to take these arrows that were originally going this way and reverse them, so move them going the other way, and then just fill in that last remaining blank. Add an arrow that goes in that direction instead. So by taking two edges and just switching them, I have been able to consider one possible neighbor of this particular configuration, and it looks like this neighbor is actually better. It looks like this probably travels a shorter distance in order to get through all the cities through this route than the current state did. And so you could imagine implementing this idea inside of a hill climbing or simulated annealing algorithm, where we repeat this process to try and take a state of this traveling salesman problem, look at all of the neighbors, and then move to the neighbors if they're better, or maybe even move to the neighbors if they're worse, until we eventually settle upon some best solution that we've been able to find. And it turns out that these types of approximation algorithms, even if they don't always find the very best solution, can often do pretty well at trying to find solutions that are helpful too. So that then was a look at local search, a particular category of algorithms that can be used for solving a particular type of problem, where we don't really care about the path to the solution. I didn't care about the steps I took to decide where the hospitals should go. I just cared about the solution itself. I just care about where the hospitals should be, or what the route through the traveling salesman journey really ought to be. Another type of algorithm that might come up are known as these categories of linear programming types of problems. And linear programming often comes up in the context where we're trying to optimize for some mathematical function, but oftentimes linear programming will come up when we might have real numbered values. So that it's not just like discrete fixed values that we might have, but any decimal values that we might want to be able to calculate. And so linear programming is a family of types of problems where we might have a situation that looks like this, where the goal of linear programming is to minimize a cost function. And you can invert the numbers and say try and maximize it, but often we'll frame it as trying to minimize a cost function that has some number of variables, x1, x2, x3, all the way up to xn, just some number of variables that are involved, things that I want to know the values to. And this cost function might have coefficients in front of those variables. And this is what we would call like a linear equation, where we just have all of these variables that might be multiplied by a coefficient and then added together. We're not going to square anything or cube anything, because that'll give us different types of equations. With linear programming, we're just dealing with linear equations in addition to linear constraints, where a constraint is going to look something like, if we sum up this particular equation that is just some linear combination of all of these variables, it is less than or equal to some bound b. And we might have a whole number of these various different constraints that we might place onto our linear programming exercise. And likewise, just as we can have constraints that are saying this linear equation is less than or equal to some bound b, it might also be equal to something. That if you want some sum of some combination of variables to be equal to a value, you can specify that. And we can also maybe specify that each variable has lower and upper bounds, that it needs to be a positive number, for example, or it needs to be a number that is less than 50, for example. And there are a number of other choices that we can make there for defining what the bounds of a variable are. But it turns out that if you can take a problem and formulate it in these terms, formulate the problem as your goal is to minimize a cost function, and you're minimizing that cost function subject to particular constraints, subject to equations that are of the form like this, of some sequence of variables is less than a bound or is equal to some particular value, then there are a number of algorithms that already exist for solving these sorts of problems. So let's go ahead and take a look at an example. Here's an example of a problem that might come up in the world of linear programming. Often this is going to come up when we're trying to optimize for something, and we want to be able to do some calculations, and we have constraints on what we're trying to optimize. And so it might be something like this. In the context of a factory, we have two machines, x1 and x2. x1 costs $50 an hour to run. x2 costs $80 an hour to run. And our goal, what we're trying to do, our objective, is to minimize the total cost. So that's what we'd like to do. But we need to do so subject to certain constraints. So there might be a labor constraint, that x1 requires 5 units of labor per hour, x2 requires 2 units of labor per hour, and we have a total of 20 units of labor that we have to spend. So this is a constraint. We have no more than 20 units of labor that we can spend, and we can spend it across x1 and x2, each of which requires a different amount of labor. And we might also have a constraint like this that tells us x1 is going to produce 10 units of output per hour, x2 is going to produce 12 units of output per hour, and the company needs 90 units of output. So we have some goal, something we need to achieve. We need to achieve 90 units of output. but there are some constraints that x1 can only produce 10 units of output per hour, x2 produces 12 units of output per hour. These types of problems come up quite frequently, and you can start to notice patterns in these types of problems. Problems where I am trying to optimize for some goal, minimizing cost, maximizing output, maximizing profits, or something like that, and there are constraints that are placed on that process. And so now we just need to formulate this problem in terms of linear equations. So let's start with this first point. Two machines, x1 and x2. X costs $50 an hour, x2 costs $80 an hour. Here we can come up with an objective function that might look like this. This is our cost function, rather. 50 times x1 plus 80 times x2, where x1 is going to be a variable representing how many hours do we run machine x1 for. x2 is going to be a variable representing how many hours are we running machine x2 for. And what we're trying to minimize is this cost function, which is just how much it costs to run each of these machines per hour summed up. This is an example of a linear equation, just some combination of these variables plus coefficients that are placed in front of them. And I would like to minimize that total value. But I need to do so subject to these constraints. x1 requires 50 units of labor per hour, x2 requires 2, and we have a total of 20 units of labor to spend. And so that gives us a constraint of this form. 5 times x1 plus 2 times x2 is less than or equal to 20. 20 is the total number of units of labor we have to spend, and that's spent across x1 and x2, each of which requires a different number of units of labor per hour, for example. And finally, we have this constraint here. x1 produces 10 units of output per hour, x2 produces 12, and we need 90 units of output. And so this might look something like this. That 10x1 plus 12x2, this is amount of output per hour, it needs to be at least 90. If we can do better, great, but it needs to be at least 90. And if you recall from my formulation before, I said that generally speaking in linear programming, we deal with equals constraints or less than or equal to constraints. So we have a greater than or equal to sign here. That's not a problem. Whenever we have a greater than or equal to sign, we can just multiply the equation by -1, and that'll flip it around to a less than or equals -90, for example, instead of a greater than or equal to 90. And that's going to be an equivalent expression that we can use to represent this problem. So now that we have this cost function and these constraints that it's subject to, it turns out there are a number of algorithms that can be used in order to solve these types of problems. And these problems go a little bit more into geometry and linear algebra than we're really going to get into. But the most popular of these types of algorithms are simplex, which was one of the first algorithms discovered for trying to solve linear programs. And later on, a class of interior point algorithms can be used to solve this type of problem as well. The key is not to understand exactly how these algorithms work, but to realize that these algorithms exist for efficiently finding solutions anytime we have a problem of this particular form. And so we can take a look, for example, at the production directory here, where here I have a file called production.py, where here I'm using SciPy, which is a library for a lot of science-related functions within Python. And I can go ahead and just run this optimization function in order to run a linear program. .linprog here is going to try and solve this linear program for me, where I provide to this expression, to this function call, all of the data about my linear program. So it needs to be in a particular format, which might be a little confusing at first. But this first argument to scipy.optimize.linprogramming is the cost function, which is in this case just an array or a list that has 50 and 80, because my original cost function was 50 times x1 plus 80 times x2. So I just tell Python 50 and 80, those are the coefficients that I am now trying to optimize for. And then I provide all of the constraints. So the constraints, and I wrote them up above in comments, is the constraint 1 is 5x1 plus 2x2 is less than or equal to 20. And constraint 2 is negative 10x1 plus negative 12x2 is less than or equal to negative 90. And so SciPy expects these constraints to be in a particular format. It first expects me to provide all of the coefficients for the upper bound equations, UB is just short for upper bound, where the coefficients of the first equation are 5 and 2, because we have 5x1 and 2x2. And the coefficients for the second equation are negative 10 and negative 12, because I have negative 10x1 plus negative 12x2. And then here, we provide it as a separate argument, just to keep things separate, what the actual bound is. What is the upper bound for each of these constraints? Well, for the first constraint, the upper bound is 20. That was constraint number 1. And then for constraint number 2, the upper bound is 90. So a bit of a cryptic way of representing it. It's not quite as simple as just writing the mathematical equations. What really is being expected here are all of the coefficients and all of the numbers that are in these equations, by first providing the coefficients for the cost function, then providing all the coefficients for the inequality constraints, and then providing all of the upper bounds for those inequality constraints. And once all of that information is there, then we can run any of these interior point algorithms or the simplex algorithm. Even if you don't understand how it works, you can just run the function and figure out what the result should be. And here I've said if the result is a success, we were able to solve this problem, go ahead and print out what the value of x1 and x2 should be. Otherwise, go ahead and print out no solution. And so if I run this program by running python production.py, it takes a second to calculate, but then we see here is what the optimal solution should be. x1 should run for 1.5 hours. x2 should run for 6.25 hours. And we were able to do this by just formulating the problem as a linear equation that we were trying to optimize, some cost that we were trying to minimize, and then some constraints that were placed on that. And many, many problems fall into this category of problems that you can solve if you can just figure out how to use equations and use these constraints to represent that general idea. And that's a theme that's going to come up a couple of times today, where we want to be able to take some problem and reduce it down to some problem we know how to solve in order to begin to find a solution and to use existing methods that we can use in order to find a solution more effectively or more efficiently. And it turns out that these types of problems, where we have constraints, show up in other ways too. And there's an entire class of problems that's more generally just known as constraint satisfaction problems. And we're going to now take a look at how you might formulate a constraint satisfaction problem and how you might go about solving a constraint satisfaction problem. But the basic idea of a constraint satisfaction problem is we have some number of variables that need to take on some values, and we need to figure out what values each of those variables should take on. But those variables are subject to particular constraints that are going to limit what values those variables can actually take on. So let's take a look at a real-world example, for example. Let's look at exam scheduling. That I have 4 students here, students 1, 2, 3, and 4. Each of them is taking some number of different classes. Classes here are going to be represented by letters. So student 1 is enrolled in courses A, B, and C. Student 2 is enrolled in courses B, D, and E, so on and so forth. And now, say a university, for example, is trying to schedule exams for all of these courses. But there are only 3 exam slots on Monday, Tuesday, and Wednesday. And we have to schedule an exam for each of these courses. But the constraint now, the constraint we have to deal with the scheduling, is that we don't want anyone to have to take 2 exams on the same day. We would like to try and minimize that or eliminate it if at all possible. So how do we begin to represent this idea? How do we structure this in a way that a computer with an AI algorithm can begin to try and solve the problem? Well, let's in particular just look at these classes that we might take and represent each of the courses as some node inside of a graph. And what we'll do is we'll create an edge between 2 nodes in this graph if there is a constraint between those 2 nodes. So what does this mean? Well, we can start with student 1, who's enrolled in courses A, B, and C. What that means is that A and B can't have an exam at the same time. A and C can't have an exam at the same time. And B and C also can't have an exam at the same time. And I can represent that in this graph by just drawing edges. One edge between A and B, one between B and C, and then one between C and A. And that encodes now the idea that between those nodes there is a constraint. And in particular, the constraint happens to be that these 2 can't be equal to each other, though there are other types of constraints that are possible, depending on the type of problem that you're trying to solve. And then we can do the same thing for each of the other students. So for student 2, who's enrolled in courses B, D, and E, well, that means B, D, and E, those all need to have edges that connect each other as well. Student 3 is enrolled in courses C, E, and F. So we'll go ahead and take C, E, and F and connect those by drawing edges between them too. And then finally, student 4 is enrolled in courses E, F, and G. And we can represent that by drawing edges between E, F, and G, although E and F already had an edge between them. We don't need another one, because this constraint is just encoding the idea that course E and course F cannot have an exam on the same day. So this, then, is what we might call the constraint graph. It is some graphical representation of all of my variables, so to speak, and the constraints between those possible variables, where in this particular case, each of the constraints represents an inequality constraint, that an edge between b and d means whatever value the variable b takes on cannot be the value that the variable d takes on as well. So what then actually is a constraint satisfaction problem? Well, a constraint satisfaction problem is just some set of variables, x1 all the way through xn, some set of domains for each of those variables. So every variable needs to take on some values. Maybe every variable has the same domain, but maybe each variable has a slightly different domain. And then there's a set of constraints, so we'll just call a set C, that is some constraints that are placed upon these variables, like x1 is not equal to x2. But they could be of other forms too, like maybe x1 equals x2 plus 1, if these variables are taking on numerical values in their domain, for example. The types of constraints are going to vary based on the types of problems. And constraint satisfaction shows up all over the place as well, in any situation where we have variables that are subject to particular constraints. So one popular game is Sudoku, for example, this 9x9 grid where you need to fill in numbers into each of these cells, but you want to make sure there's never a duplicate number in any row or in any column or in any grid of 3x3 cells, for example. So what might this look like as a constraint satisfaction problem? Well, my variables are all of the empty squares in the puzzle. So represented here is just like an x comma y coordinate, for example, as all of the squares where I need to plug in a value, where I don't know what value it should take on. The domain is just going to be all of the numbers from 1 through 9, any value that I could fill in to one of these cells. So that is going to be the domain for each of these variables. And then the constraints are going to be of the form like this cell can't be equal to this cell, can't be equal to this cell, can't be. All these need to be different, for example. And same for all of the rows and the columns and the 3x3 squares as well. So those constraints are going to enforce what values are actually allowed. And we can formulate the same idea in the case of this exam scheduling problem, where the variables we have are the different courses, A up through G. The domain for each of these variables is going to be Monday, Tuesday, and Wednesday. Those are the possible values each of the variables can take on that in this case just represent when is the exam for that class. And then the constraints are of this form. A is not equal to B, A is not equal to C, meaning A and B can't have an exam on the same day, A and C can't have an exam on the same day, or more formally, these two variables cannot take on the same value within their domain. So that then is this formulation of a constraint satisfaction problem that we can begin to use to try and solve this problem. And constraints can come in a number of different forms. There are hard constraints, which are constraints that must be satisfied for a correct solution. So something like in the Sudoku puzzle, you cannot have this cell and this cell that are in the same row take on the same value. That is a hard constraint. But problems can also have soft constraints, where these are constraints that express some notion of preference, that maybe A and B can't have an exam on the same day, but maybe someone has a preference that A's exam is earlier than B's exam. It doesn't need to be the case, but there's some expression that some solution is better than another solution. And in that case, you might formulate the problem as trying to optimize for maximizing people's preferences. You want people's preferences to be satisfied as much as possible. In this case, though, we'll mostly just deal with hard constraints, constraints that must be met in order to have a correct case, though, we'll mostly just, so we want to figure out some assignment of these variables to their particular values that is ultimately going to give us a solution to the problem by allowing us to assign some day to each of the classes such that we don't have any conflicts between classes. So it turns out that we can classify the constraints in a constraint satisfaction problem into a number of different categories. The first of those categories are perhaps the simplest of the types of constraints, which are known as unary constraints, where a unary constraint is a constraint that just involves a single variable. For example, a unary constraint might be something like A does not equal Monday, meaning course A cannot have its exam on Monday. If for some reason the instructor for the course isn't available on Monday, you might have a constraint in your problem that looks like this, something that just has a single variable A in it, and maybe says A is not equal to Monday, or A is equal to something, or in the case of numbers, greater than or less than something, a constraint that just has one variable we consider to be a unary constraint. And this is in contrast to something like a binary constraint, which is a constraint that involves two variables, for example. So this would be a constraint like the ones we were looking at before, something like A does not equal B, is an example of a binary constraint because it is a constraint that has two variables involved in it, a and b, and we represented that using some arc or some edge that connects variable a to variable b. And using this knowledge of, OK, what is a unary constraint, what is a binary constraint, there are different types of things we can say about a particular constraint satisfaction problem. And one thing we can say is we can try and make the problem node consistent. So what does node consistency mean? Node consistency means that we have all of the values in a variable's domain satisfying that variable's unary constraints. So for each of the variables inside of our constraint satisfaction problem, if all of the values satisfy the unary constraints for that particular variable, we can say that the entire problem is node consistent, or we can even say that a particular variable is node consistent if we just want to make one node consistent within itself. So what does that actually look like? Let's look at now a simplified example where instead of having a whole bunch of different classes, we just have two classes, A and B, each of which has an exam on either Monday or Tuesday or Wednesday. So this is the domain for the variable A, and this is the domain for the variable B. And now let's imagine we have these constraints. A not equal to Monday, B not equal to Tuesday, B not equal to Monday, A not equal to B. So those are the constraints that we have on this particular problem. And what we can now try to do is enforce node consistency. And node consistency just means we make sure that all of the values for any variable's domain satisfy its unary constraints. And so we could start by trying to make node A node consistent. Like, is it consistent? Does every value inside of A's domain satisfy its unary constraints? Well, initially we'll see that Monday does not satisfy A's unary constraints because we have a constraint, a unary constraint here, that A is not equal to Monday, but Monday is still in A's domain. And so this is something that is not node consistent because we have Monday in the domain, but this is not a valid value for this particular node. And so how do we make this node consistent? Well, to make the node consistent, what we'll do is we'll just go ahead and remove Monday from A's domain. Now A can only be on Tuesday or Wednesday because we had this constraint that said A is not equal to Monday. And at this point now, A is node consistent. For each of the values that A can take on, Tuesday and Wednesday, there is no constraint that is a unary constraint that conflicts with that idea. There is no constraint that says that A can't be Tuesday. There's no unary constraint that says that A cannot be on Wednesday. And so now we can turn our attention to B. B also has a domain, Monday, Tuesday, and Wednesday. And we can begin to see whether those variables satisfy the unary constraints as well. Well, here's a unary constraint. B is not equal to Tuesday. And that does not appear to be satisfied by this domain of Monday, Tuesday, and Wednesday, because Tuesday, this possible value that the variable B could take on, is not consistent with this unary constraint, that B is not equal to Tuesday. So to solve that problem, we'll go ahead and remove Tuesday from B's domain. Now B's domain only contains Monday and Wednesday, but as it turns out, there's yet another unary constraint that we placed on the variable B, which is here. B is not equal to Monday. That means that this value, Monday, inside of B's domain, is not consistent with B's unary constraints, because we have a constraint that says that B cannot be Monday, and so we can remove Monday from B's domain. And now we've made it through all of the unary constraints. We've not yet considered this constraint, which is a binary constraint. But we've considered all of the unary constraints, all of the constraints that involve just a single variable. And we've made sure that every node is consistent with those unary constraints. So we can say that now we have enforced node consistency, that for each of these possible nodes, we can pick any of these values in the domain, and there won't be a unary constraint that is violated as a result of it. So node consistency is fairly easy to enforce. We just take each node, make sure the values in the domain satisfy the unary constraints. Where things get a little bit more interesting is when we consider different types of consistency, something like arc consistency, for example. And arc consistency refers to when all of the values in a variable's domain satisfy the variable's binary constraints. So when we're looking at trying to make A arc consistent, we're no longer just considering the unary constraints that involve A. We're trying to consider all of the binary constraints that involve A as well. So any edge that connects A to another variable inside of that constraint graph that we were taking a look at before. Put a little bit more formally, arc consistency, and arc really is just another word for like an edge that connects two of these nodes inside of our constraint graph. We can define arc consistency a little more precisely like this. In order to make some variable x arc consistent, with respect to some other variable y, we need to remove any element from x's domain to make sure that every choice for x, every choice in x's domain, has a possible choice for y. So put another way, if I have a variable x and I want to make x arc consistent, then I'm going to look at all of the possible values that x can take on and make sure that for all of those possible values, there is still some choice that I can make for y, if there's some arc between x and y, to make sure that y has a possible option that I can choose as well. So let's look at an example of that. Going back to this example from before, we enforced node consistency already by saying that A can only be on Tuesday or Wednesday, because we knew that A could not be on Monday. And we also said that B's only domain only consists of Wednesday, because we know that B does not equal Tuesday, and also B does not equal Monday. So now let's begin to consider arc consistency. Let's try and make A arc consistent with B. And what that means is to make A arc consistent with respect to B means that for any choice we make in A's domain, there is some choice we can make in B's domain that is going to be consistent. And we can try that. For A, we can choose Tuesday as a possible value for A. If I choose Tuesday for A, is there a value for B that satisfies the binary constraint? Well, yes, B Wednesday would satisfy this constraint that A does not equal B, because Tuesday does not equal Wednesday. However, if we chose Wednesday for A, well, then there is no choice in B's domain that satisfies this binary constraint. There is no way I can choose something for B that satisfies A does not equal B, because I know B must be Wednesday. And so if ever I run into a situation like this, where I see that here is a possible value for A, such that there is no choice of value for B that satisfies the binary constraint, well, then this is not arc consistent. And to make it arc consistent, I would need to take Wednesday and remove it from A's domain, because Wednesday was not going to be a possible choice I could make for A, because it wasn't consistent with this binary constraint for B. There was no way I could choose Wednesday for A and still have an available solution by choosing something for B as well. So here now I've been able to enforce arc consistency. And in doing so, I've actually solved this entire problem, that given these constraints where A and B can have exams on either Monday or Tuesday or Wednesday, the only solution, as it would appear, is that A's exam must be on Tuesday and B's exam must be on Wednesday. And that is the only option available to me. So if we want to apply our consistency to a larger graph, not just looking at one particular pair of our consistency, there are ways we can do that too. And we can begin to formalize what the pseudocode would look like for trying to write an algorithm that enforces our consistency. And we'll start by defining a function called revise. Revise is going to take as input a CSP, otherwise known as a constraint satisfaction problem, and also two variables x and y. And what revise is going to do is it is going to make x arc consistent with respect to y, meaning remove anything from x's domain that doesn't allow for a possible option for y. How does this work? Well, we'll go ahead and first keep track of whether or not we've made a revision. Revise is ultimately going to return true or false. It'll return true in the event that we did make a revision to x's domain. It'll return false if we didn't make any change to x's domain. And we'll see in a moment why that's going to be helpful. But we start by saying revised equals false. We haven't made any changes. Then we'll say, all right, let's go ahead and loop over all of the possible values in x's domain. So loop over x's domain for each little x in x's domain. I want to make sure that for each of those choices, I have some available choice in y that satisfies the binary constraints that are defined inside of my CSP, inside of my constraint satisfaction problem. So if ever it's the case that there is no value y in y's domain that satisfies the constraint for x and y, well, if that's the case, that means that this value x shouldn't be in x's domain. So I'll go ahead and delete x from x's domain, and I'll set revised equal to true, because I did change x's domain. I changed x's domain by removing little x, and I removed little x because it wasn't arc consistent. There was no way I could choose a value for y that would satisfy this xy constraint. So in this case, we'll go ahead and set revised equal true. And we'll do this again and again for every value in x's domain. Sometimes it might be fine. In other cases, it might not allow for a possible choice for y, in which case we need to remove this value from x's domain. And at the end, we just return revised to indicate whether or not we actually made a change. So this function then, this revised function, is effectively an implementation of what you saw me do graphically a moment ago, and it makes one variable, x, arc consistent with another variable, in this case y. But generally speaking, when we want to enforce arc consistency, we'll often want to enforce arc consistency not just for a single arc, but for the entire constraint satisfaction problem. And it turns out there's an algorithm to do that as well, and that algorithm is known as AC3. AC3 takes a constraint satisfaction problem, and it enforces arc consistency across the entire problem. How does it do that? Well, it's going to basically maintain a queue, or basically just a line, of all of the arcs that it needs to make consistent. And over time, we might remove things from that queue as we begin dealing with arc consistency, and we might need to add things to that queue as well if there are more things we need to make arc consistent. So we'll go ahead and start with a queue that contains all of the arcs in the constraint satisfaction problem, all of the edges that connect two nodes that have some sort of binary constraint between them. And now, as long as the queue is non-empty, there is work to be done. The queue is all of the things that we need to make arc consistent. So as long as the queue is non-empty, there's still things we have to do. What do we have to do? Well, we'll start by dequeuing from the queue. Remove something from the queue. And strictly speaking, it doesn't need to be a queue, but a queue is a traditional way of doing this. We'll dequeue from the queue, and that'll give us an arc, x and y, these two variables where I would like to make x arc consistent with y. So how do we make x arc consistent with y? Well, we can go ahead and just use that revise function that we talked about a moment ago. We call the revise function, passing as input the constraint satisfaction problem, and also these variables x and y, because I want to make x arc consistent with y. In other words, remove any values from x's domain that don't leave an available option for y. And recall, what does revised return? Well, it returns true if we actually made a change, if we removed something from x's domain because there wasn't an available option for y, for example. And it returns false if we didn't make any change to x's domain at all. And it turns out if revised returns false, if we didn't make any changes, well, then there's not a whole lot more work to be done here for this arc. We can just move ahead to the next arc that's in the queue. But if we did make a change, if we did reduce x's domain by removing values from x's domain, well, then what we might realize is that this creates potential problems later on, that it might mean that some arc that was arc consistent with x, that node might no longer be arc consistent with x, because while there used to be an option that we could choose for x, now there might not be, because now we might have removed something from x that was necessary for some other arc to be arc consistent. And so if ever we did revise x's domain, we're going to need to add some things to the queue, some additional arcs that we might want to check. How do we do that? Well, first thing we want to check is to make sure that x's domain is not 0. If x's domain is 0, that means there are no available options for x at all. And that means that there's no way you can solve the constraint satisfaction problem. If we've removed everything from x's domain, we'll go ahead and just return false here to indicate there's no way to solve the problem because there's nothing left in x's domain. But otherwise, if there are things left in x's domain, but fewer things than before, well, then what we'll do is we'll loop over each variable z that is in all of x's neighbors except for y. Y we already handled. But we'll consider all of x's others neighbors and ask ourselves, all right, well, that arc from each of those z's to x, that arc might no longer be arc consistent. Because while for each z, there might have been a possible option we could choose for x to correspond with each of z's possible values, now there might not be because we removed some elements from x's domain. And so what we'll do here is we'll go ahead and enqueue, adding something to the queue, this arc zx for all of those neighbors z. So we need to add back some arcs to the queue in order to continue to enforce arc consistency. At the very end, if we make it through all this process, then we can return true. But this now is AC3, this algorithm for enforcing arc consistency on a constraint satisfaction problem. And the big idea is really just keep track of all of the arcs that we might need to make arc consistent, make it arc consistent by calling the revise function. And if we did revise it, then there are some new arcs that might need to be added to the queue in order to make sure that everything is still arc consistent, even after we've removed some of the elements from a particular variable's domain. So what then would happen if we tried to enforce arc consistency on a graph like this, on a graph where each of these variables has a domain of Monday, Tuesday, and Wednesday? Well, it turns out that by enforcing arc consistency on this graph, while it can solve some types of problems, nothing actually changes here. For any particular arc, just considering two variables, there's always a way for me to just, for any of the choices I make for one of them, make a choice for the other one, because there are three options, and I just need the two to be different from each other. So this is actually quite easy to just take an arc and just declare that it is arc consistent, because if I pick, Monday for D, then I just pick something that isn't Monday for B. In arc consistency, we only consider consistency between a binary constraint between two nodes, and we're not really considering all of the rest of the nodes yet. So just using AC3, the enforcement of arc consistency, that can sometimes have the effect of reducing domains to make it easier to find solutions, but it will not always actually solve the problem. We might still need to somehow search to try and find a solution. And we can use classical traditional search algorithms to try to do so. You'll recall that a search problem generally consists of these parts. We have some initial state, some actions, a transition model that takes me from one state to another state, a goal test to tell me, have I satisfied my objective correctly, and then some path cost function, because in the case of maze solving, I was trying to get to my goal as quickly as possible. So you could formulate a CSP, or a constraint satisfaction problem, as one of these types of search problems. The initial state will just be an empty assignment, where an assignment is just a way for me to assign any particular variable to any particular value. So if an empty assignment is no variables are assigned to any values yet, then the action I can take is adding some new variable equals value pair to that assignment, saying for this assignment, let me add a new value for this variable. And the transition model just defines what happens when you take that action. You get a new assignment that has that variable equal to that value inside of it. The goal test is just checking to make sure all the variables have been assigned and making sure all the constraints have been satisfied. And the path cost function, sort of irrelevant. I don't really care about what the path really is. I just care about finding some assignment that actually satisfies all of the constraints. So really, all the paths have the same cost. I don't really care about the path to the goal. I just care about the solution itself, much as we've talked about now before. The problem here, though, is that if we just implement this naive search algorithm just by implementing breadth first search or depth first search, this is going to be very, very inefficient. And there are ways we can take advantage of efficiencies in the structure of a constraint satisfaction problem itself. And one of the key ideas is that we can really just order these variables, and it doesn't matter what order we assign variables in. The assignment a equals 2 and then b equals 8 is identical to the assignment of b equals 8 and then a equals 2. Switching the order doesn't really change anything about the fundamental nature of that assignment. And so there are some ways that we can try and revise this idea of a search algorithm to apply it specifically for a problem like a constraint satisfaction problem. And it turns out the search algorithm we'll generally use when talking about constraint satisfaction problems is something known as backtracking search. And the big idea of backtracking search is we'll go ahead and make assignments from variables to values. And if ever we get stuck, we arrive at a place where there is no way we can make any forward progress while still preserving the constraints that we need to enforce, we'll go ahead and backtrack and try something else instead. So the very basic sketch of what backtracking search looks like is it looks like this. Function called backtrack that takes as input an assignment and a constraint satisfaction problem. So initially, we don't have any assigned variables. So when we begin backtracking search, this assignment is just going to be the empty assignment with no variables inside of it. But we'll see later, this is going to be a recursive function. So backtrack takes as input the assignment and the problem. If the assignment is complete, meaning all of the variables have been assigned, we just return that assignment. That, of course, won't be true initially, because we start with an empty assignment. But over time, we might add things to that assignment. So if ever the assignment actually is complete, then we're done. Then just go ahead and return that assignment. But otherwise, there's some work to be done. So what we'll need to do is select an unassigned variable for this particular problem. So we need to take the problem, look at the variables that have already been assigned, and pick a variable that has not yet been assigned. And I'll go ahead and take that variable. And then I need to consider all of the values in that variable's domain. So we'll go ahead and call this domain values function. We'll talk a little more about that later. That takes a variable and just gives me back an ordered list of all of the values in its domain. So I've taken a random unselected variable. I'm going to loop over all of the possible values. And the idea is, let me just try all of these values as possible values for the variable. So if the value is consistent with the assignment so far. It doesn't violate any of the constraints. Well, then let's go ahead and add variable equals value to the assignment because it's so far consistent. And now let's recursively call backtrack to try and make the rest of the assignments also consistent. So I'll go ahead and call backtrack on this new assignment that I've added the variable equals value to. And now I recursively call backtrack and see what the result is. And if the result isn't a failure, well, then let me just return that result. And otherwise, what else could happen? Well, if it turns out the result was a failure, well, then that means this value was probably a bad choice for this particular variable, because when I assigned this variable equal to that value, eventually down the road, I ran into a situation where I violated constraints. There was nothing more I could do. So now I'll remove variable equals value from the assignment, effectively backtracking to say, all right, that value didn't work. Let's try another value instead. And then at the very end, if we were never able to return a complete assignment, we'll just go ahead and return failure, because that means that none of the values worked for this particular variable. This now is the idea for backtracking search, to take each of the variables, try values for them, and recursively try backtracking search, see if we can make progress. And if ever we run into a dead end, we run into a situation where there is no possible value we can choose that satisfies the constraints, we return failure, and that propagates up, and eventually we make a different choice by going back and trying something else instead. So let's put this algorithm into practice. Let's actually try and use backtracking search to solve this problem now, where I need to figure out how to assign each of these courses to an exam slot on Monday or Tuesday or Wednesday in such a way that it satisfies these constraints, that each of these edges mean those two classes cannot have an exam on the same day. So I can start by just starting at a node. Doesn't really matter which I start with, but in this case, I'll just start with A. And I'll ask a question like, all right, let me loop over the values in the domain. And maybe in this case, I'll just start with Monday and say, all right, let's go ahead and assign A to Monday. We'll just go in order Monday, Tuesday, Wednesday. And now let's consider node B. All right, so I've made an assignment to A, so I recursively call backtrack with this new part of the assignment. Now I'm looking to pick another unassigned variable like B. And I'll say, all right, maybe I'll start with Monday, because that's the very first value in B's domain. And I ask, all right, does Monday violate any constraints? And it turns out, yes, it does. It violates this constraint here between A and B, because A and B are now both on Monday. And that doesn't work, because B can't be on the same day as A. So that doesn't work. So we might instead try Tuesday, try the next value in B's domain. And is that consistent with the assignment so far? Well, yeah, B Tuesday, A Monday, that is consistent so far, because they're not on the same day. So that's good. Now we can recursively call backtrack, try again. Pick another unassigned variable, something like D, and say, all right, let's go through its possible values. Is Monday consistent with this assignment? Well, yes, it is. B and D are on different days, Monday versus Tuesday, and A and B are also on different days, Monday versus Tuesday. So that's fine so far, too. We'll go ahead and try again. Maybe we'll go to this variable here, E. Say, can we make that consistent? Let's go through the possible values. We've recursively called backtrack. We might start with Monday and say, all right, that's not consistent, because D and E now have exams on the same day. So we might try Tuesday instead, going to the next one. Ask, is that consistent? Well, no, it's not, because B and E, those have exams on the same day. And so we try, all right, is Wednesday consistent? And it turns out, all right, yes, it is. Wednesday is consistent because D and E now have exams on different days. B and E now have exams on different days. All seems to be well so far. I recursively call backtrack, select another unassigned variable. We'll say maybe choose C this time. And say, all right, let's try the values that C could take on. Let's start with Monday. And it turns out that's not consistent, because now A and C both have exams on the same day. So I try Tuesday and say that's not consistent either, because B and C now have exams on the same day. And then I say, all right, let's go ahead and try Wednesday. But that's not consistent either, because C and E each have exams on the same day too. So now we've gone through all of the possible values for C, Monday, Tuesday, and Wednesday, and none of them are consistent. There is no way we can have a consistent assignment. Backtrack in this case will return failure. And so then we'd say, all right, we have to backtrack back to here. Well, now for E, we've tried all of Monday, Tuesday, and Wednesday, and none of those work, because Wednesday, which seemed to work, turned out to be a failure. So that means there's no possible way we can assign E. So that's a failure too. We have to go back up to D, which means that Monday assignment to D, that must be wrong. We must try something else. So we can try, all right, what if instead of Monday, we try Tuesday? Tuesday, it turns out, is not consistent, because B and D now have an exam on the same day. But Wednesday, as it turns out, works. And now we can begin to make some forward progress again. We go back to E and say, all right, which of these values works? Monday turns out to work by not violating any constraints. Then we go up to C now. Monday doesn't work because it violates a constraint. Violates 2, actually. Tuesday doesn't work because it violates a constraint as well. But Wednesday does work. Then we can go to the next variable F and say, all right, does Monday work? Well, no, it violates a constraint. But Tuesday does work. And then finally, we can look at the last variable, G, recursively calling backtrack one more time. Monday is inconsistent. That violates a constraint. Tuesday also violates a constraint. But Wednesday, that doesn't violate a constraint. And so now at this point, we recursively call backtrack one last time. We now have a satisfactory assignment of all of the variables. And at this point, we can say that we are now done. We have now been able to successfully assign a variable or a value to each one of these variables in such a way that we're not violating any constraints. We're going to go ahead and have classes A and E have their exams on Monday. Classes B and F can have their exams on Tuesday. And classes C, D, and G can have their exams on Wednesday. And there's no violated constraints that might come up there. So that then was a graphical look at how this might work. Let's now take a look at some code we could use to actually try and solve this problem as well. So here I'll go ahead and go into the scheduling directory. We're here now. We'll start by looking at schedule0.py, where here I define a list of variables, A, B, C, D, E, F, G. Those are all of the different classes. Then underneath that, I define my list of constraints. So constraint A and B, that is a constraint because they can't be on the same day. Likewise, A and C, B and C, so on and so forth, enforcing those exact same constraints. And here, then, is what the backtracking function might look like. First, if the assignment is complete, if I've made an assignment of every variable to a value, go ahead and just return that assignment. Then we'll select an unassigned variable from that assignment. Then for each of the possible values in the domain, Monday, Tuesday, Wednesday, let's go ahead and create a new assignment that assigns the variable to that value. I'll call this consistent function, which I'll show you in a moment, that just checks to make sure this new assignment is consistent. But if it is consistent, we'll go ahead and call backtrack to go ahead and continue trying to run backtracking search. And as long as the result is not none, meaning it wasn't a failure, we can go ahead and return that result. But if we make it through all the values and nothing works, then it is a failure. There's no solution. We go ahead and return none here. What do these functions do? Select unassigned variable is just going to choose a variable not yet assigned. So it's going to loop over all the variables. And if it's not already assigned, we'll go ahead and just return that variable. And what does the consistent function do? Well, the consistent function goes through all the constraints. And if we have a situation where we've assigned both of those values to variables, but they are the same, well, then that is a violation of the constraint, in which case we'll return false. But if nothing is inconsistent, then the assignment is consistent and will return true. And then all the program does is it calls backtrack on an empty assignment, an empty dictionary that has no variable assigned and no values yet, save that inside a solution, and then print out that solution. So by running this now, I can run Python schedule0.py. And what I get as a result of that is an assignment of all these variables to values. And it turns out we assigned A to Monday as we would expect, B to Tuesday, C to Wednesday, exactly the same type of thing we were talking about before, an assignment of each of these variables to values that doesn't violate any constraints. And I had to do a fair amount of work in order to implement this idea myself. I had to write the backtrack function that went ahead and went through this process of recursively trying to do this backtracking search. But it turns out the constraint satisfaction problems are so popular that there exist many libraries that already implement this type of idea. Again, as with before, the specific library is not as important as the fact that libraries do exist. This is just one example of a Python constraint library where now, rather than having to do all the work from scratch inside of schedule1.py, I'm just taking advantage of a library that implements a lot of these ideas already. So here, I create a new problem, add variables to it with particular domains. I add a whole bunch of these individual constraints where I call add constraint and pass in a function describing what the constraint is. And the constraint basically says it's a function that takes two variables, x and y, and makes sure that x is not equal to y, enforcing the idea that these two classes cannot have exams on the same day. And then, for any constraint satisfaction problem, I can call getSolutions to get all the solutions to that problem. And then for each of those solutions, print out what that solution happens to be. And if I run python schedule1.py, I now see there are actually a number of different solutions that can be used to solve the problem. There are in fact 6 different solutions, assignments of variables to values, that will give me a satisfactory answer to this constraint satisfaction problem. So this then was an implementation of a very basic backtracking search method, where really we just went through each of the variables, picked one that wasn't assigned, tried the possible values the variable could take on, and then if it worked, if it didn't violate any constraints, then we kept trying other variables. And if ever we hit a dead end, we had to backtrack. But ultimately, we might be able to be a little bit more intelligent about how we do this in order to improve the efficiency of how we solve these sorts of problems. And one thing we might imagine trying to do is going back to this idea of inference, using the knowledge we know to be able to draw conclusions in order to make the rest of the problem-solving process a little bit easier. And let's now go back to where we got stuck in this problem the first time. When we were solving this constraint satisfaction problem, we dealt with B, and then we went on to D, and we went ahead and just assigned D to Monday, because that seemed to work with the assignment so far. It didn't violate any constraints. But it turned out that later on, that choice turned out to be a bad one, that choice wasn't consistent with the rest of the values that we could take on here. And the question is there anything we could do to avoid getting into a situation like this, avoid trying to go down a path that's ultimately not going to lead anywhere by taking advantage of knowledge that we have initially? And it turns out we do have that kind of knowledge. We can look at just the structure of this graph so far, and we can say that right now, C's domain, for example, contains values Monday, Tuesday, and Wednesday. And based on those values, we can say that this graph is not arc consistent. Recall that arc consistency is all about making sure that for every possible value for a particular node, that there is some other value that we are able to choose. And as we can see here, Monday and Tuesday are not going to be possible values that we can choose for C. They're not going to be consistent with a node like B, for example, because B is equal to Tuesday, which means that C cannot be Tuesday. And because A is equal to Monday, C also cannot be Monday. So using that information, by making C arc consistent with A and B, we could remove Monday and Tuesday from C's domain and just leave C with Wednesday, for example. And if we continued to try and enforce arc consistency, we'd see there are some other conclusions we can draw as well. We see that B's only option is Tuesday and C's only option is Wednesday. And so if we want to make E arc consistent, well, E can't be Tuesday, because that wouldn't be arc consistent with B. And E can't be Wednesday, because that wouldn't be arc consistent with C. So we can go ahead and say E and just set that equal to Monday, for example. And then we can begin to do this process again and again, that in order to make D arc consistent with B and E, then D would have to be Wednesday. That's the only possible option. And likewise, we can make the same judgments for F and G as well. And it turns out that without having to do any additional search, just by enforcing arc consistency, we were able to actually figure out what the assignment of all the variables should be without needing to backtrack at all. And the way we did that is by interleaving this search process and the inference step, by this step of trying to enforce arc consistency. And the algorithm to do this is often called just the maintaining arc consistency algorithm, which just enforces arc consistency every time we make a new assignment of a value to an existing variable. So sometimes we can enforce arc consistency using that AC3 algorithm at the very beginning of the problem, before we even begin searching, in order to limit the domain of the variables in order to make it easier to search. But we can also take advantage of the interleaving of enforcing arc consistency with search, such that every time in the search process we make a new assignment, we go ahead and enforce arc consistency as well to make sure that we're just eliminating possible values from domains whenever possible. And how do we do this? Well, this is really equivalent to just every time we make a new assignment to a variable x, we'll go ahead and call our AC3 algorithm, this algorithm that enforces arc consistency on a constraint satisfaction problem. And we go ahead and call that, starting it with a queue, not of all of the arcs, which we did originally, but just of all of the arcs that we want to make arc consistent with x, this thing that we have just made an assignment to. So all arcs y, x, where y is a neighbor of x, something that shares a constraint with x, for example. And by maintaining arc consistency in the backtracking search process, we can ultimately make our search process a little bit more efficient. And so this is the revised version of this backtrack function. Same as before, the changes here highlighted in yellow. Every time we add a new variable equals value to our assignment, we'll go ahead and run this inference procedure, which might do a number of different things. But one thing it could do is call the maintaining arc consistency algorithm to make sure we're able to enforce arc consistency on the problem. And we might be able to draw new inferences as a result of that process, get new guarantees of this variable needs to be equal to that value, for example. That might happen one time. It might happen many times. And so long as those inferences are not a failure, as long as they don't lead to a situation where there's no possible way to make forward progress, well, then we can go ahead and add those inferences, those new knowledge, that new pieces of knowledge I know about what variables should be assigned to what values. I can add those to the assignment in order to more quickly make forward progress by taking advantage of information that I can just deduce, information I know based on the rest of the structure of the constraint satisfaction problem. And the only other change I'll need to make now is if it turns out this value doesn't work, well then down here I'll go ahead and need to remove not only variable equals value, but also any of those inferences that I made, remove that from the assignment as well. And so here then, we're often able to solve the problem by backtracking less than we might originally have needed to, just by taking advantage of the fact that every time we make a new assignment of one variable to one value, that might reduce the domains of other variables as well. And we can use that information to begin to more quickly draw conclusions in order to try and solve the problem more efficiently as well. And it turns out there are other heuristics we can use to try and improve the efficiency of our search process as well. And it really boils down to a couple of these functions that I've talked about, but we haven't really talked about how they're working. And one of them is this function here, select unassigned variable, where we're selecting some variable in the constraint satisfaction problem that has not yet been assigned. So far, I've sort of just been selecting variables randomly, just like picking one variable and one unassigned variable in order to decide, all right, this is the variable that we're going to assign next, and then going from there. But it turns out that by being a little bit intelligent, by following certain heuristics, we might be able to make the search process much more efficient just by choosing very carefully which variable we should explore next. So some of those heuristics include the minimum remaining values, or MRV heuristic, which generally says that if I have a choice between which variable I should select the variable with the smallest domain, the variable that has the fewest number of remaining values left. With the idea being, if there are only 2 remaining values left, well, I may as well prune one of them very quickly in order to get to the other, because one of those 2 has got to be the solution if a solution does exist. Sometimes minimum remaining values might not give a conclusive result if all the nodes have the same number of remaining values, for example. And in that case, another heuristic that can be helpful to look at is the degree heuristic. The degree of a node is the number of nodes that are attached to that node, the number of nodes that are constrained by that particular node. And if you imagine which variable should I choose? Should I choose a variable that has a high degree, that is connected to a lot of different things? Or a variable with a low degree that is not connected to a lot of different things? Well, it can often make sense to choose the variable that has the highest degree, that is connected to the most other nodes, as the thing you would search first. Why is that the case? Well, it's because by choosing a variable with a high degree, that is immediately going to constrain the rest of the variables more, and it's more likely to be able to eliminate large sections of the state space that you don't need to search through at all. So what could this actually look like? Let's go back to this search problem here. In this particular case, I've made an assignment here, I've made an assignment here, and the question is, what should I look at next? And according to the minimum remaining values heuristic, what I should choose is the variable that has the fewest remaining possible values. And in this case, that's this node here, node C, that only has one variable left in this domain, which in this case is Wednesday, which is a very reasonable choice of a next assignment to make, because I know it's the only option, for example. I know that the only possible option for C is Wednesday, so I may as well make that assignment and then potentially explore the rest of the space after that. But meanwhile, at the very start of the problem, when I didn't have any knowledge of what nodes should have what values yet, I still had to pick what node should be the first one that I try and assign a value to. And I arbitrarily just chose the one at the top, node A, originally. But we can be more intelligent about that. We can look at this particular graph. All of them have domains of the same size, domain of size 3. So minimum remaining values doesn't really help us there. But we might notice that node E has the highest degree. It is connected to the most things. And so perhaps it makes sense to begin our search, rather than starting at node A at the very top, start with the node with the highest degree. Start by searching from node E, because from there, that's going to much more easily allow us to enforce the constraints that are nearby, eliminating large portions of the search space that I might not need to search through. And in fact, by starting with E, we can immediately then assign other variables. And following that, we can actually assign the rest of the variables without needing to do any backtracking at all, even if I'm not using this inference procedure, just by starting with a node that has a high degree that is going to very quickly restrict the possible values that other nodes can take on. So that then is how we can go about selecting an unassigned variable in a particular order. Rather than randomly picking a variable, if we're a little bit intelligent about how we choose it, we can make our search process much, much more efficient by making sure we don't have to search through portions of the search space that ultimately aren't going to matter. The other variable we haven't really talked about, the other function here, is this domain values function. This domain values function that takes a variable and gives me back a sequence of all of the values inside of that variable's domain. The naive way to approach it is what we did before, which is just go in order. Go Monday, then Tuesday, then Wednesday. But the problem is that going in that order might not be the most efficient order to search in. That sometimes it might be more efficient to choose values that are likely to be solutions first, and then go to other values. Now, how do you assess whether a value is likelier to lead to a solution or less likely to lead to a solution? Well, one thing you can take a look at is how many constraints get added, how many things get removed from domains as you make this new assignment of a variable to this particular value. And the heuristic we can use here is the least constraining value heuristic, which is the idea that we should return variables in order based on the number of choices that are ruled out for neighboring values. And I want to start with the least constraining value, the value that rules out the fewest possible options. And the idea there is that if all I care about doing is finding a solution, if I start with a value that rules out a lot of other choices, I'm ruling out a lot of possibilities that maybe is going to make it less likely that this particular choice leads to a solution. Whereas on the other hand, if I have a variable and I start by choosing a value that doesn't rule out very much, well, then I still have a lot of space where there might be a solution that I could ultimately find. And this might seem a little bit counterintuitive and a little bit at odds with what we were talking about before, where I said when you're picking a variable, you should pick the variable that is going to have the fewest possible values remaining. But here I want to pick the value for the variable that is the least constraining. But the general idea is that when I am picking a variable, I would like to prune large portions of the search space by just choosing a variable that is going to allow me to quickly eliminate possible options. Whereas here, within a particular variable, as I'm considering values that that variable could take on, I would like to just find a solution. And so what I want to do is ultimately choose a value that still leaves open the possibility of me finding a solution to be as likely as possible. By not ruling out many options, I leave open the possibility that I can still find a solution without needing to go back later and backtrack. So an example of that might be in this particular situation here, if I'm trying to choose a variable for a value for node C here, that C is equal to either Tuesday or Wednesday. We know it can't be Monday because it conflicts with this domain here, where we already know that A is Monday. So C must be Tuesday or Wednesday. And the question is, should I try Tuesday first or should I try Wednesday first? And if I try Tuesday, what gets ruled out? Well, one option gets ruled out here. A second option gets ruled out here. And a third option gets ruled out here. So choosing Tuesday would rule out 3 possible options. And what about choosing Wednesday? Well, choosing Wednesday would rule out one option here, and it would rule out one option there. And so I have 2 choices. I can choose Tuesday that rules out 3 options, or Wednesday that rules out 2 options. And according to the least constraining value heuristic, what I should probably do is go ahead and choose Wednesday, the one that rules out the fewest number of possible options, leaving open as many chances as possible for me to eventually find a solution inside of this state space. And ultimately, if you continue this process, we will find a solution, an assignment of variables to values that allows us to give each of these exams, each of these classes, an exam date that doesn't conflict with anyone that happens to be enrolled in 2 classes at the same time. So the big takeaway now with all of this is that there are a number of different ways we can formulate a problem. The ways we've looked at today are we can formulate a problem as a local search problem, a problem where we're looking at a current node and moving to a neighbor based on whether that neighbor is better or worse than the current node that we are looking at. We looked at formulating problems as linear programs, where just by putting things in terms of equations and constraints, we're able to solve problems a little bit more efficiently. And we saw formulating a problem as a constraint satisfaction problem, creating this graph of all of the constraints that connect two variables that have some constraint between them, and using that information to be able to figure out what the solution should be. And so the takeaway of all of this now is that if we have some problem in artificial intelligence that we would like to use AI to be able to solve, whether that's trying to figure out where hospitals should be, or trying to solve the traveling salesman problem, trying to optimize productions and costs and whatnot, or trying to figure out how to satisfy certain constraints, whether that's in a Sudoku puzzle, or whether that's in trying to figure out how to schedule exams for a university, or any number of a wide variety of types of problems, if we can formulate that problem as one of these sorts of problems, then we can use these known algorithms, these algorithms for enforcing art consistency and backtracking search, these hill climbing and simulated annealing algorithms, these simplex algorithms and interior point algorithms that can be used to solve linear programs, that we can use those techniques to begin to solve a whole wide variety of problems, all in this world of optimization inside of artificial intelligence. This was an introduction to artificial intelligence with Python for today. We will see you next time.